What is dietary fiber? Dietary fiber is a form of complex carbohydrate that is edible and is found in plants. It is resistant to digestion in the stomach and small intestine, but it is partially fermented in the large intestine. The human body lacks the necessary enzymes to completely digest it. Although dietary fibers are relatively low in calories, they take up more space in the digestive tract than other foods, creating a feeling of fullness and promoting early satiety. Dietary fiber can be classified based on two characteristics, which is soluble fiber and insoluble fiber. Soluble fiber is the fiber attracts water to it and dissolves in it, creating a material that resembles gel. It slows down the digestive process, which delays and reduces the absorption of carbohydrates and fats into the blood. Slowing down the digestive process gives enough time for large enough stool to develop. The example sources of soluble fiber are apple, carrot, barley, beans, and many more. Dietary fiber that is insoluble in water is referred to as insoluble fiber. It may be present in plant cell walls and is mostly unaltered when it travels through the gastrointestinal tract. This kind of fiber gives the stool bulk and aids in promoting regular bowel motions. The body cannot absorb or break down insoluble fiber, so it does not contain many calories or nutrients. Instead, it works to support gut health and help with digestion. Nuts, beans, green beans, potatoes, wheat bran, and whole wheat flour are excellent sources of insoluble fiber. Next, let's move on to non-enzymatic gravimetric method. The determination of dietary fiber in food plays a crucial role in evaluating its nutritional composition and health benefits. Non-enzymatic gravimetric method, known as crude fiber method, is one commonly employed method for estimating the indigestible fiber content in food. This method involves subjecting a food sample to a standardized treatment with dilute acid and alkali to selectively solubilize digestible carbohydrates, proteins, and lipids. The resulting insoluble residue is collected by filtration, tried with ash, and quantized gravimetrically. The remaining residue is primarily composed of lignin and cellulose, representing the crude fiber content of the food. The crude fiber method primarily focuses on isolating the indigestible components of dietary fiber, namely cellulose and lignin, by subjecting the food sample to sequential extraction with 1.25% of sulfuric acid, which is dilute acid, and 1.25% of sodium hydroxide, which is alkali. The acid treatment hydrolyzes carbohydrates and proteins, while the alkali treatment saponifies fatty acids present in the sample. Consequently, cellulose and lignin, being insoluble, remain as the major components in the residue. It is important to note that hemicellulose and pectin, which are also dietary fiber components, are solubilized during this process. Thus, it cannot be detected using the crude fiber method. Crude fiber content is equal to A minus B grams divided by weight of sample multiplied by 100, where A is insoluble residue that is collected by filtration, dry and weighed, and B is the ashing conducted, cool and weighed. Next, enzymatic gravimetric method. The AOAC methods are a set of standardized analytical procedures used in food analysis. Enzymatic gravimetric method is a laboratory technique that is used to determine content of dietary fiber in food samples. It provides a quantitative measurement of total dietary content. Enzymatic gravimetric method is to analyze dietary fiber content, which is based on selectively breaking down of non-fiber components using enzymes. The remaining insoluble fiber is measured using gravimetric techniques, which the enzymes involved will help to isolate the dietary fiber that targets protein, starch, and lipid. The enzymatic gravimetric method provides a reliable and accurate measure to determine the amount of dietary fiber in food samples with following principle. Firstly, enzymatic digestion. This enzyme used specifically to break down proteins, starches, and lipids that are not categorized as dietary fiber. Secondly, filtration. After digestion, the sample is filtered to separate the insoluble dietary fiber from the soluble fiber. Next, washing. The residue from insoluble fiber inside filter is washed to remove any residual enzymes or soluble fiber. Then, drying. The washed insoluble fiber residue is dried to remove moisture. Last but not least, gravimetric measurement. The dried residue is then weighed using analytical balance, which the weight shows the amount of dietary fiber present in the sample. Here is the formula of dietary fiber content. Next, we move on to sample preparation. Our first sample we use is a banana. Here are 6 steps in banana sample preparation. Bananas that are ripe and indicative of the batch or of the population were picked. Size, color, and texture are taken into account among other things. The edible portion of the bananas had its peel removed. The fruit was then cut with a stainless steel paring knife into 1 centimeter thick slices, immediately frozen in liquid nitrogen and homogenized in liquid nitrogen using a 6-liter. This can be done using a blender or food processor to create a uniform sample. To produce a consistent sample, use a blender or food processor. Then, a suitable portion of the homogenized banana sample was weighed. Depending on the demands of the technology being used and the necessary level of precision, the precise weight will be determined. Next step, the weighed banana sample was added to particular enzymes that target the dietary fiber component. Depending on the methodology being used, different enzymes may be employed. The enzyme-containing sample was incubated for the specified amount of time and temperature. Step 5. Filtration and washing. The sample was filtered to separate the insoluble residue from the liquid after the enzymatic treatment. To get rid of any soluble components, the residue was washed with water or other suitable solvents. Lastly, step 6. The residue was dried and weighed. To get rid of any moisture left over, the filtered residue was dried. Depending on the specifications of the method being utilized, either an oven or a freeze-drying technique can be employed for this. And to assess the amount of dietary fiber present in the sample, the dried residue of the banana was weighed. Other than that, cauliflower are used as a sample. Here are 4 steps in cauliflower sample preparation. Cauliflower that are fresh produce was procured from a local supermarket. Size, color, and texture are taken into account, among other things. Next, the florets were removed and steamed until tender, drained, and cooled to room temperature. The material was chopped finely, weighed, and lyophilized with wet and dry weights recorded. The recovered dry weight of steamed cauliflower was 11.1%. The third step is homogenize. A sample, which is approximately to 300 grams, was ground in a natriumulate homogenizer followed by further grinding in a grinding mill until 100% passed through a 0.5 mm sieve. Lastly is storage. The ground material was thoroughly mixed in a plastic bag by inversion and transferred and stored in well-sealed Duran glass bottles at room temperature away from direct sunlight. Next, the English scumming method. This method is a specific analytical technique for determining non-starch polysaccharides in plant foods using gas chromatography. It involved the enzymatic and chemical treatment of the sample to isolate and convert the different fiber components into the constituent sugars, which are then analyzed using gas chromatography. Here is a step-by-step overview of the method. Firstly, sample preparation. The plant food sample is prepared by removing any non-fibrous components and grinding it into a fine powder. Second, enzymatic hydrolysis. The sample is subjected to enzymatic hydrolysis using a mixture of specific enzymes. These enzymes break down the complex polysaccharides into their constituent monosaccharides. Next, filtration. After hydrolysis, the sample is filtered to remove any insoluble residues. Next, derivatization. The released monosaccharides are then derivatized into aldehyde acetates. This process involves converting the monosaccharides into their corresponding aldehydes and then acetylating them with acetic anhydride. Next, gas chromatography. The derivatized monosaccharides are separated and quantified using gas chromatography. The gas chromatograph separates the different aldehyde acetates based on their chemical properties, and a detector measures their abundance. Calibration. To determine the concentration of each monosaccharide, calibration curves are constructed using known standards of individual sugars. Last but not least, calculation. The concentrations of the individual sugars are then used to calculate the total non-starch polysaccharide content in the sample. Next, we look on the principle of English scumming method. A defected food sample is heated in water to gelatinize the starch. Enzymes are then added to digest the starch and proteins. Pure ethanol is added to the solution to precipitate the fiber, which is separated from the digest by centrifugation and is then washed and dried. The fiber is then hydrolyzed using a concentrated sulfuric acid solution to break it down into its constituent monosaccharides.